All right, today we learned the Fenwick tree, also called binary indexed tree, or bit. The problem, you have an array, you want prefix sum queries and point updates. Both need to be fast. Simple array gives O of n for queries. Prefix sum array gives O of n for updates. Fenwick tree gives O of log n for both. And the code is just a few lines. Core concept. Each position in the BIT stores a partial sum. The range depends on the binary representation of the index. The magic formula is I and negative I. This gives the lowest set bit, or LSB. Position I stores the sum from index I minus LSB of I plus 1 to index I. Examples: BIT at 1 stores A at 1 only. BIT at 2 stores sum of A at 1 to 2. BIT at 4 stores sum of A at 1 to 4. BIT at 8 stores sum of A at 1 to 8. Odd indices store single elements. Powers of 2 store larger ranges. Why I and negative I works. In 2's complement, negative I flips all bits and adds 1. Example with I equals 6. 6 in binary is 0, 1, 1, 0. Negative 6 is 1, 0, 1, 0. 6 and negative 6 is 0, 0, 1, 0 equals 2. So LSB of 6 is 2. This tells us BIT at 6 covers 2 elements. Update operation. To add delta to index I, start at I, add delta to BIT at I, move to next by adding LSB of I to I. Repeat until I exceeds n. Example, updating index 3. 3 goes to 4, goes to 8, goes to 16. We update BIT cells 3, 4, 8. That is log n cells. Query operation. To get prefix sum from 1 to I, start at I with sum equals 0. Add BIT at I to sum. Subtract LSB of I from I. Repeat until I equals 0. Example, querying index 7. 7 goes to 6, goes to 4, goes to 0. Sum equals BIT at 7 plus BIT at 6 plus BIT at 4. Only 3 additions for 7 elements. Range query. Sum from L to R equals query of R minus query of L minus 1. Still O of log n. Code structure. LSB function, return I and negative I. Update function, while I less than or equal to n, BIT at I plus equals delta. I plus equals LSB of I. Query function, sum equals 0, while I greater than 0, sum plus equals BIT at I minus equals LSB of I. Return sum. That is the entire implementation, about 10 lines. Complexity. Build O of n log n, update O of log n, query O of log n, space O of n. Simpler and uses less memory than segment tree. Applications. Counting inversions, cumulative frequency tables, range sum queries with updates, competitive programming. Closing. The Fenwick tree is elegant. 1-bit trick I and negative I powers everything. Update moves forward by adding LSB. Query moves backward by subtracting LSB. Memorize these 2 operations. The rest follows naturally.